Now let's talk about this J-type instruction data and control path, which should be simpler than I-type. Little involvement is there for the push and pop operation. We'll explain that, but it's kind of manageable. So let's start with a simple jump instruction, JMP or J, right? It's opcode and 26 bit of address. All right. So what in this processor, what we are assuming, this is kind of an uh, direct addressing with upper 6 bit as zeros. Okay, upper 6 bit as zeros. So we need to have that means from your instruction memory or instruction register, uh, depending on what type of circuit you are making there, data path you are making there. But let's say for timing it is coming directly from the instruction memory, and this data 32 bit, out of that we are picking up 26 bit, lower 26 bit, and doing a 6 bit 0 extender, passing it through a 6 bit 0 extender to make it a 32 bit. So this is again very simple circuit. Upper 6 bit, that line is grounded, that makes you 32 bit address. And now since the PC's native path like PC plus 1, you have two options now, either PC plus 1 or update the PC with the address given inside the instruction. So you need to place a multiplexer there. Simple. Now let's talk about another little complex on top of this. It is JL. Before that, jump instruction control, right? What are the control? You have this memory read and write. For the instruction memory, of course, this is read only part, will involve only the read signals there. And address selection 3 as a multiplexer, address selection between PC plus 1 and your 26 bit address. So this is the control, JMP control. Now JL, it is okay, PC plus, so PC equals your address, that is like a jump, but additionally what it does, register 31, it adds, it stores the content PC plus 1. Okay, so to make this functionality happens, what we need to do, we'll keep the data path for the jump instruction. Only additional thing we need to make sure, your register 31, which is write address, is connected to a fixed 31 value, and write data is coming in this case from the PC plus 1, like this adder, which is resulting in the PC plus 1 value. From that we are drawing that value, we are getting that value and connecting it into the write data of the register file. So that becomes your JL instruction data path, and control being of course additional to your J instruction control signals. We have additional register write and read control signal to write the PC plus 1 into the register 31. So that's your JL instruction control. Now stack instruction data path. So we have two operations, push and pop. Just to recall, their functionality is push is like we have this stack pointer, right? And memory pointed by the stack pointer, you read from register 0 and stored that content to the memory which is pointed by your stack pointer, and then decrease the stack pointer by 1. Pop is just the reverse operation. You first increase the stack pointer by 1 and write the R0, register 0, with the memory content, memory address being pointed by stack pointer. So in this case, we don't use at all this 0 to 25, that address. This is kind of don't care. We only, based on the opcode, we perform push and pop. So that means what happens here, for push, we need to read from registered 0. So that's how why R1 address is connected to a constant 0, and R1 data being connected to the data in, because I need to write that data into the data memory, where the address is coming from the stack pointer. Okay, and then in the same way we need to decrease the stack pointer value. That means stack pointer current value need to fade into as one of the operand of the ALU, and a constant 1 being fed into the other operand of the ALU, and operation being subtraction here, and that subtraction result will coming from the ALU and going into the stack pointer to be loaded after the memory read is done. Now pop, on the other hand, can use the same data path except for the writing of the data, right? So pop is first you take the stack pointer value, add with 1 and load it into the stack pointer, and then you read the data memory from that stack pointer address, updated stack pointer address, and write the data back into the register file for register 0. So your write address should be connected to 0 and write data will be coming from the data out. So for this data path. And control, of course, stack pointer load, register files, register read and write, for the data memory read and write, and ALU operation. For push it will be a subtraction, for pop it will be an addition. So this is your stack instruction control path. So now to make a combined JType instruction data path, we keep on superimposing on top of each other those data path, and if there is a data source conflict, we resolve it by multiplexer. So now we have like a multiplexer in the data like between 31 and 0, 31 for your JL instruction, 0 for your push, pop operation on the write address, right? And then write data, either it can come from the PC plus 1 for the JL instruction, or pop from the data memory for the pop instruction. So there is one more multiplexer involved, and we already talked about the other multiplexer involved with the program counter. And of course this becomes your different control signal. We start naming the multiplexer, new multiplexer control signals, and that becomes your JType instruction control signal paths. So they are all coming from your controller. Now we do the complex thing, right? We superimpose R-type, I-type, J-type data path with an assumption instruction memory and data memory are separate. That becomes like this path, okay, lot of multiplexer. So remember I told you that multiplexer is one of the important component in constructing microprocessor. Here you can see it in live that there are a lot of multiplexer involved here, okay. So you superimpose. If there are any additional data conflict, we start putting the multiplexer there to conflict the data source, to resolve the conflict data source. For your project, though, it is things a little bit different from this, especially from the memory perspective. Remember, like we have the memory separate out from the processor part, so that means we should not show the memory in the data path diagram, and also we need to involve instruction register now to make sure that we are using one single memory, not a separate memory for data and on instruction, but one single memory act as storage for both instructions and data in that. So that's why we need to introduce an instruction register in between. And anything, if you look at like couple of instruction like data out, so this is going out for the memory to be written in, and this data in is coming from the memory to be to consume inside the processor in terms of either it is storing in the register file or do something else as needed. So it's like that, and the address which is computed from the ALU, it is going to the memory, okay. And look at this address is for read and write, of course, but it has also two potential data, actually three potential data source, this address or the memory. One is, of course, from the PC plus 1. Okay, this part is PC plus 1. That's the data source, which is like basically your current program counter. So don't be confused with PC plus 1 statement. It is your current program counter from which you need to fetch the instruction. Another is your stack pointer for push and pop operation. Another is from the ALU source, which is for your store word, load word, the memory calculation, address calculation coming from the ALU. So that is your another source of address for going towards the memory, right? So we have three potential data source there. One is from the ALU, another from the stack pointer, another from the program counter. So we need to deploy two multiplexers there to select correct address at the correct phase of operation. So we'll discuss also this this important aspect of now how the controller controls all this control signal through the separate phases. Like remember, we have 5-step execution: instruction fetch, decode, execute, memory, and write back. And we'll see in that discussion how we can actually construct systematically what controller will do at different steps, different of this 5-step. What should controller produce at control signal, so that all the things basically your instruction being processed in completion. Okay, so let's say you are providing something like your program is stored in the memory and you are fetching the instruction. That's the first instruction being add R1, R2, R3. So how through the different steps, these 5 steps, instruction fetch, decode, execute, memory, and write back, how it changed the control signal of the various part of this processor, especially this multiplexer control signals and all the other components control signals, so that overall at the end of this 5-stage cycle you perform that add R1, R2, R3. Okay, we'll see that.